Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
1927 Wolfgang Pauli on the connection between the theory of relativity and quantum mechanics. The year 1927 represented a crucible, a forge wherein some of the most fundamental concepts underlying modern physics were hammered into shape. It was a period of feverish innovation, a time when a nascent field of quantum mechanics, still wrestling with its own paradoxical nature, began to tentatively reach out and intertwine with the established pillar of Albert Einstein's theory of relativity. Wolfgang Pauli, a man whose reputation for intellectual rigor was rivaled only by his sharp wit and occasionally acerbic commentary, played a pivotal role in this intellectual engagement. His 1927 paper on the connection between the theory of relativity and quantum mechanics, a work that, while perhaps overshadowed by some of his other contributions, merits a position of considerable significance, serves as a crucial bridge between these two monumental theories. Before Pauli's contribution, the intellectual atmosphere teemed with a sense of unfinished business. Quantum mechanics, birthed in the early decades of the 20th century through the work of Planck, Einstein, Bohr, Heisenberg, and Schrödinger, had achieved remarkable successes explaining atomic phenomena, yet its initial formulations were fundamentally non-relativistic. They treated time and space as absolute backgrounds, and therefore they struggled to incorporate the elegant principles of Einstein's theory. Special relativity, introduced in 1905, had, after all, revolutionized our understanding of space and time, establishing the equivalence of mass and energy, and dictating the constancy of the speed of light. The need to reconcile these two seemingly disparate frameworks was becoming increasingly pressing. The seeds of Pauli's work were sown in the earlier developments. The Klein-Gordon equation, proposed independently by Oscar Klein and Walter Gordon, represented a first attempt to formulate a relativistic wave equation. This equation, applied to spin-zero particles, such as the pi meson, successfully incorporated special relativity. However, the Klein-Gordon equation possessed certain inherent problems. Specifically, the probability density derived from it was, rather disconcertingly, shown to admit negative values, thus leading to difficulties interpreting the wave function as a probability amplitude. Furthermore, it failed to adequately describe the behavior of particles possessing an intrinsic angular momentum, particles that were later confirmed to possess. The quest for a relativistic quantum mechanical description capable of accounting for the electron's spin was critical. The electron, with its intrinsic angular momentum and its associated magnetic moment, was known to exhibit behaviors that the original Schrödinger equation, with its non-relativistic underpinnings, would entirely accommodate. This was not merely a theoretical curiosity. Experimental observations, such as the Stern-Gerlach experiment, confirmed the existence of the electron spin, demanding a theoretical framework that incorporated it. Pauli's work directly addressed this gap. The fundamental insight that guided Pauli, and the core of his contribution, was the introduction of a two-component wave function to describe a spin-half particle, such as the electron. This wave function, often represented as a column matrix comprised of two complex numbers, acted as the foundation for what became known as the Pauli equation, and it provided, for all practical purposes, a more complete picture. He introduced a set of two x2 matrices, the Pauli matrices, which are represented by the Greek symbol sigma, with three subscripts representing the three axes of space. These matrices, together with the identity matrix, formed the basis for describing. The Pauli matrices possess some exceedingly interesting properties. They anticommute, meaning that when multiplied in different orders, the result varies by a minus sign. Their eigenvalues are plusone and minusone, neatly reflecting the two possible spin states of an electron. The Pauli equation, which emerged, successfully incorporates the spin of the electron in a relativistic manner, eliminating the negative probabilities and providing an accurate description of the electron's behavior in the presence of electromagnetic fields. The equation describes how the electron behaves and interacts with the electromagnetic field. This was a critical achievement. The paper itself is a compact, highly focused piece of work. The narrative is not convoluted, yet it is thorough. Pauli presents his mathematical derivation with a characteristic blend of clarity and elegance, ensuring that the core ideas are communicated with maximum efficiency. The specific techniques employed included the use of spinor algebra, an approach that offered a natural way of incorporating spin into the relativistic framework. It is important to note that Pauli possessed a profound understanding of mathematics. This was not merely a matter of applying known formulas. He possessed the expertise to invent new ones, to manipulate them, and to interpret their physical significance. The immediate impact of this work was, and remains, considerable. The Pauli equation rapidly became an essential tool for theoretical physicists. It provided a crucial framework for understanding atomic spectra, the interaction of electrons with magnetic fields, and in the development of more advanced theories, it offered a relativistic account of electron behavior, paving a way for the development of quantum electrodynamics, the quantum field theory of electromagnetism, which emerged in the late 1940s. The applications also extended beyond the immediate realm of atomic physics, any area where the behavior of spin-half particles was crucial, be it in condensed matter physics or nuclear physics, relied on the insights and the equations derived by Pauli. His approach represented a significant step toward a complete and consistent theory of quantum mechanics. The paper's reception, while certainly positive, was also somewhat nuanced, reflecting the ongoing evolution of quantum mechanics. Some researchers, particularly those deeply immersed in the mathematical formalism, recognized the profound implications of the work immediately. Others, accustomed to other approaches, took longer to fully appreciate the value of Pauli's methods. There were debates, the usual consequence of intellectual ferment, regarding the precise interpretation of the wave functions or the philosophical impact of the new quantum mechanics. Ultimately, however, the weight of experimental confirmation and the consistent results obtained with the Pauli equation secured its place in the pantheon of physics equations. The work was built upon by Dirac in his seminal 1998 paper. Dirac, inspired by Pauli's work, went one step further. Dirac developed the Dirac equation, a fully relativistic wave equation for spin-half particles. Dirac's equation predicted the existence of antiparticles, specifically the positron, a particle with the same mass as an electron but with a positive electric charge. This prediction was then confirmed experimentally. Dirac, in essence, expanded on the Pauli equation, but the latter's role as a foundational step remains undeniable. Dirac's work would have perhaps been impossible without Pauli's insights. The influence extended to other researchers. Both Heisenberg and Jordan, key figures in the development of quantum mechanics, recognized the significance of Pauli's work. They incorporated his insights into their own explorations of quantum field theory and the development of the matrix formalism, which remains a central concept in particle physics. The influence of Pauli, both direct and indirect, permeated the field. Pauli's contributions were, and remain, subject to further refinement. The Pauli equation, for example, is a non-interacting theory, meaning it does not account for the effects of electron-electron interactions in a completely rigorous manner. Later developments in quantum electrodynamics, and more fundamentally, the conceptualization and mathematical formulation of quantum field theory, allowed for a more complete treatment of these interactions. Furthermore, the extension of Pauli's work to describe other particles and the application of these concepts to understand strongly interacting particles, such as quarks, provided for a deeper understanding. Yet, Pauli's initial work, its elegance, efficacy, continue to hold their own even. One of the critical turning points in understanding Pauli's work is to appreciate the broader historical context. The 1990s were, after all, a period of intense collaboration and cross-fertilization of ideas. The intellectual landscape that shaped Pauli's work was not entirely determined by abstract mathematical constructs. It was also driven by the intense debates and the synergistic interactions among a group of brilliant physicists from various disciplines. Pauli, for all his intellect, was not entirely alone. He was in constant dialogue with his peers. His many friends and interlocutors included such intellectual giants as Niels Bohr, Werner Heisenberg, Max Born, and Enrico Fermi. These individuals, and others, were driven by a shared desire to understand the fundamental laws of nature. This collaborative spirit provided the critical environment that gave rise to Pauli's insights. The influence ran both ways, from earlier works to Pauli's, and then from Pauli's work itself to later contributions. Dirac's work represented a direct consequence. Heisenberg's focus on the uncertainty principle and his work on the theory of the matrix were equally influenced. Furthermore, the advances in quantum electrodynamics, particularly the work of Feynman, Schwingber and Tominaga, during the late 1940s and early 1950s, built on the foundations laid by Pauli's. Pauli's work served as a crucial stepping stone. It was more than simply a modification of the Schrödinger equation. It was a new way of thinking about the relationship between quantum mechanics and relativity, a way that paved the path for subsequent breakthroughs. It was a synthesis, a merging of theoretical frameworks that, to this day, underpins the structure of our understanding of fundamental particles. The enduring legacy of Wolfgang Pauli's 1927 paper rests on several pillars. It showed that spin could be incorporated into relativistic quantum mechanics. It provided a powerful formalism, the Pauli equation, It allowed for accurate predictions about the behavior of electrons. It established a vital connection between relativity and quantum mechanics, a connection that was only strengthened by later research. Furthermore, it stimulated other researchers to expand on his ideas, driving the development of quantum field theory. The very character of the work itself, the elegance of the formalism, the clarity of the mathematical derivations, and the conceptual insights, all of these reasons cemented its place in the history of physics. It is a testament to the enduring impact of brilliant minds at work. It also serves as a reminder that scientific progress is a collaborative effort, a process of building upon the insights of those who have come before. Pauli's work remains a vivid demonstration of the power of rigorous thought, innovative mathematical techniques, and the unrelenting pursuit of understanding the universe that surrounds us. And so, we can say that Pauli's contribution of 1927 remains a classic, a cornerstone, and a testament to the power of intellectual inquiry.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.